In this video, we will continue our discussion of spontaneous processes by calculating entropy changes. Although entropy is a measure of the dispersal of energy of a reaction in a thermodynamic system, we really need to know the change in entropy between products and reactants to tell if the entropy increases or decreases in a system. Also, there is another variable that measures if a reaction is spontaneous or not, which is Gibbs free energy, or the available energy of a system. What is the universe? It is everything we see around us, and that which we cannot see but can only imagine. Well, for the sake of this chemistry class, there are two parts to every universe. The system is what is being studied. If you are boiling water, the system is the water, and the surroundings are everything else around the system. For our boiling water example, the surroundings are the pot, the oven, and even you. We define the universe by saying that it is the system plus the surroundings. This is the same for entropy as well. The overall change in the entropy of a universe as a result of a chemical or physical process equals the change in entropy of the system plus the change in entropy of the surroundings. A positive delta S universe is another way of expressing the second law of thermodynamics. The second law of thermodynamics is heat always flows spontaneously from hotter to colder bodies, and never the reverse, unless external work is performed on the system. This, therefore, implies that if a process is reversed, then the spontaneity is also reversed, which leads to two rules. 1. If delta S universe is positive, then a reaction is spontaneous. 2. If delta S universe is negative, then a reaction is non-spontaneous. If you ignite ethene, an important precursor of plastics, at temperatures below 100 degrees Celsius, this would be an example of a spontaneous reaction that needs a small outside force to get it started. The formula of ethene is C2H4, and if you combust it with oxygen, the products will be CO2 and H2O. The reaction will be written as C2H4 gas plus 3O2 gas results in 2 CO2 gas plus 2 H2O liquid. As written, this reaction consumes 4 moles of gas and produces 2 moles of gas. To predict the entropy change of this reaction, think about the entropy change of the gas particles. They are going to have a large entropy because they have the most dispersed energy. The liquid parts of the equation will have much smaller entropies. So, since we are producing less moles of gas than we are consuming, the change in entropy of the system will decrease. If this is a spontaneous reaction, we know that the delta S universe is positive and the delta S of the system is negative. To compensate for the negative delta S of the system, we must have a large positive delta S of the surroundings, which we do because this is a highly exothermic reaction. There is a lot of heat produced, which will disperse the energy of the surroundings. Another way to write the delta S of the surroundings is that it equals the negative of the change in enthalpy of the system divided by the temperature of the system. Enthalpy is defined as the heat or thermal energy exchanged at constant pressure. In our ethane example, the heat that was released as a result of the combustion is the enthalpy. The change in enthalpy equals the heat that is lost or gained by the system at constant pressure. Endothermic processes involve a transfer of thermal energy, heat, from the surroundings into the system. If the system is isolated from the surroundings, as in a styrofoam cup, the system will experience a decrease in temperature. However, delta H for the system is still positive for an endothermic process, so therefore, if you were to touch an endothermic reaction, the temperature would decrease. Exothermic processes involve a transfer of thermal energy, heat, from the system to the surroundings. If the system is isolated from the surroundings, as in a styrofoam cup, the system will experience an increase in temperature. However, delta H for the system is still negative for an exothermic process, so if you were to touch an exothermic reaction, the temperature would increase. A way to calculate entropy changes is by an equation that equals the difference between the sum of the entropies of the products and the sum of the entropies of the reactants at 25 degrees Celsius. The standard delta S of the reaction equals the product of all the coefficients of the individual products times their standard entropies summed, minus the product of all the coefficients of the reactants times their standard entropies summed. In the above reaction, N and M are the coefficients of the products and the reactants in the balanced equation. Calculating delta S of the universe is not a convenient way to determine if a reaction is spontaneous or not, so we will introduce a new term to determine if a reaction is spontaneous. Gibbs free energy, which is represented by a delta capital G, or the available energy of a reaction. Delta G equals the change in enthalpy of a reaction minus the temperature times the change in entropy of a reaction. It is named after Josiah Gibbs, an American scientist who was instrumental in promoting chemistry as a rigorous deductive science. This equation is easy to derive from our delta S of the universe discussion. Delta S of the universe equals delta S of the system plus delta S of the surroundings. Delta S of the surroundings equals negative delta H of the system divided by the temperature. Plug this value of delta S of the surroundings into the equation and rearrange, and you find that negative temperature times delta S of the universe equals the delta H of the system minus the temperature times the delta S of the system. This means that temperature times delta S of the universe is equivalent to the negative of Gibbs free energy. Remember our rules of delta S of the universe determining spontaneity? What do you think this means for our delta G determining spontaneity? We will discuss this soon. Another way to think about Gibbs free energy is that it is the available energy to do work. For our ethane example, the Gibbs free energy is the amount of energy that is stored in the ethane and oxygen molecules ready to be released to do work. A way to calculate the change in Gibbs free energy is by using an equation that equals the difference between the sum of the Gibbs free energies of the products and the sum of the Gibbs free energies of the reactants at 25 degrees Celsius. The standard delta G of the reaction equals the product of all the coefficients of the individual products times their standard changes in Gibbs free energies of formation summed minus the products of all the coefficients of the reactants times their standard changes in Gibbs free energies of formation summed. In the above reaction, N and M are the coefficients of the products and the reactants in the balanced equation. Let us run through some scenarios concerning delta G, delta H, and delta S. If delta H is negative, this indicates an exothermic reaction and heat is being released from the system. Since the universe always tends toward lower energy, if the system is releasing heat, this is thermodynamically favored. If delta S is positive, this means that the energy is dispersed and the entropy of the system increases. Again, this is thermodynamically favored. So let's plug both of these signs into our delta G equals delta H minus T delta S equation. A negative delta H will make the delta G negative, and if we subtract something positive from a negative number, we will have an even bigger negative number. So a negative delta G indicates a spontaneous reaction in the forward reaction. Let's investigate this equation using the opposite scenario. If delta H is positive, this indicates an endothermic reaction, and heat is being absorbed into the system. Since the universe always tends toward lower energy, if the system is absorbing heat, this is not thermodynamically favored. If delta S is negative, this means that the energy is becoming more constrained, and the entropy of the system decreases. Again, this is not thermodynamically favored. So let's plug both of these signs into our delta G equals delta H minus T delta S equation. A positive delta H will make the delta G positive, and if we subtract something negative from a positive number, we will have an even bigger positive number. So a positive delta G indicates a non-spontaneous reaction in the forward reaction. This leads us to two important rules regarding Gibbs free energy. 1. If delta G is negative, then a reaction is written as spontaneous. 2. If delta G is positive, then a reaction is written as non-spontaneous. Why do I keep saying as written and in the forward direction? This is because chemical reactions can be reversed. If they are reversed, then the signs of delta H, delta S, and delta G of the reactions are also reversed, and therefore the spontaneity of the reactions is reversed. But there are other scenarios for this equation. Consider a chemical cold pack, which contains ammonium nitrate in a separate packet and some water. When you break the packet containing ammonium nitrate, the ions of ammonium nitrate are mixed with the water, which increases the dispersion of the system and means that the entropy is positive. But we said it was a cold pack. Endothermic reactions absorb heat from the surroundings and have positive delta H. Endothermic reactions also feel cold to the touch because the surroundings are losing heat to the system. So this reaction has a positive delta H and a positive delta S. What will happen to the delta G? The Gibbs free energy equation does have one more variable in it, temperature. so this process becomes temperature dependent. But obviously this is a spontaneous reaction because the cold packs can get cold. We need our delta G to be negative for this to be a spontaneous reaction. So let's analyze this equation to see what would make our delta G negative. If our delta H is positive, then this would cause our delta G to also be positive. To make our delta G negative, we would need a bigger number than our delta H to subtract from our delta H. Since our delta S is positive, this is possible if we have a large temperature, which means this reaction is going to be spontaneous at high temperatures. But this is an ice pack, you say, which means cold. But we don't know how high the temperature has to be to make this a spontaneous reaction. In this case, it appears that the cold of the ice pack is warm enough to make this reaction a spontaneous reaction. Let's make a table to see how these different situations relate together. In our table, we have the variables delta H and delta S. In our table, we have the different scenarios: always spontaneous, never spontaneous, or spontaneous at high temperatures. And in the boxes that correspond to the variables for these scenarios, we have their possible values. There are two sometimes spontaneous scenarios: the one with the ice pack we just discussed, and the opposite, where delta H and delta S are both negative. Pause the video now to see if you can fill in the table correctly for this final row. If you said this reaction was spontaneous at low temperatures, you were correct. This is because we need our delta G negative for this to be a spontaneous reaction. If our delta H is negative, then this would cause our delta G to also be negative. But we are also subtracting a negative number from our negative delta H, so this could possibly make our delta G positive. Therefore, we need a smaller number than our delta H to subtract from our delta H to make our delta G positive. This is possible if we have a small temperature, which means this reaction is going to be spontaneous at low temperatures. To find the boiling temperature for a substance, if you know the standard delta H of fusion and standard delta S, you can use the fact that when a substance boils, the standard delta G equals 0. All the standard means is that the substances are at their standard state at 1 atmosphere. This is because the system is at equilibrium when a substance boils, and at equilibrium, delta G equals 0. In our equation, if the standard delta G equals 0, then the standard delta H equals temperature times the standard delta S. Solve for temperature, which will equal standard delta H divided by standard delta S. This equation will only work, however, if standard delta H and standard delta S do not change much with changing temperature. After all this talk about Gibbs free energy, you might be asking yourself, what does it really mean? Free energy is a measure of the maximum amount of work that can be released during a chemical process. For an example process, let's consider an internal combustion engine of a car. We will rearrange our free energy equation to solve for delta H. This will look like delta H equals delta G plus temperature times delta S. This means there are two parts to the total amount of energy that comes from making and breaking chemical bonds in the combustion equation. One part, delta G, is the amount of theoretical energy that can be converted into useful work, such as generating electricity for the car's electrical system. The other part is the T delta S energy that is not usable. This is the portion of the energy that disperses out the car's exhaust system as hot gases. In fact, only about 30% of the energy produced during combustion of a gasoline-powered car is useful work. The rest of the total energy is wasted. Now we will work on some problems using the concepts discussed in this video. Calculate delta S naught reaction for the following reaction at 25 degrees Celsius. 2 SO2 gas plus O2 gas results in 2 SO3 gas. Given these values, S naught for SO2 gas equals 248.2 joules per mole Kelvin. S naught for O2 gas equals 205.0 joules per mole Kelvin, and S naught for SO3 gas equals 256.8 joules per mole Kelvin. The equation to solve this problem is the equation we introduced for solving entropy changes. Every thermodynamic variable, delta G, delta H, and delta S, has the exact same equation, but we will be concentrating on the delta S version. The standard delta S of the reaction equals the product of all the coefficients of the individual products times their standard entropies summed minus the product of all the coefficients of the reactions times their standard entropy summed. For this reaction, we have two reactants, but only one product. So the first part of this equation will just be the coefficient of SO3 times the S0 value for SO3 gas. This equals 2 moles times 256.8 joules per mole Kelvin, which equals 513.6 joules per Kelvin. Subtracted from this number are the sum of the two reactant coefficients multiplied by their respective S0 values. This will be 2 moles times 248.2 joules per mole times Kelvin for SO2 gas, and 1 mole times 205.0 joules per mole Kelvin for the O2 gas. This equals 701.4 joules per Kelvin. To find the delta S0 reaction, subtract the reactants from the products. This will equal 513.6 joules per Kelvin minus 701.4 joules per Kelvin, which equals negative 187.8 joules per Kelvin. Calculate delta S universe for the synthesis of ammonia at 25 degrees Celsius if delta S system equals negative 199 joules per Kelvin and delta H system equals negative 92.6 kilojoules. Is this reaction spontaneous at 25 degrees Celsius? Delta S of the universe equals delta S of the system plus delta S of the surroundings. Delta S of the surroundings equals the negative delta enthalpy of the system divided by the temperature of the system. So let's think about units for this calculation. The units of delta S of the system are joules per Kelvin, and the units of delta H of the system are kilojoules, and the units of temperature is degrees Celsius. We will convert the units of temperature to Kelvin and the units of delta H to joules, but you will get the same answer if you convert the units of delta S to kilojoules per Kelvin. First, convert 25 degrees Celsius to Kelvin by adding 273.15, which equals 298.15 Kelvin. Then convert negative 92.6 kilojoules to joules by multiplying by 1,000. So we have negative 92,600 joules. Plug your values into your new equation, which is delta S of the universe equals delta S of the system minus delta H of the system divided by the temperature. So we have negative 199 joules per Kelvin minus negative 92,600 joules divided by 298.15. This equals negative 199 joules per Kelvin minus negative 310.58 joules per Kelvin. The final answer is then 111.58, or rounded to 3 sig figs, 112 joules per Kelvin. A positive delta S of the universe means a spontaneous reaction, so therefore this reaction is spontaneous. For a particular reaction, delta H reaction equals 53.0 kilojoules and delta S reaction equals 115 joules per Kelvin. Calculate the delta G reaction at A, 25 degrees Celsius, and B, 250 degrees Celsius. C, at which temperature is the reaction spontaneous? The equation you want to use for this problem is delta G equals delta H minus T times delta S. But first, let's analyze the different scenarios they give us with the table we developed before the signs of these variables. Since both delta H of the reaction and delta S of the reaction are positive, we need to look at the line of the table where both are positive. This line tells us that this reaction is sometimes spontaneous, and it will be spontaneous at high temperatures. So we need to determine if this reaction is spontaneous at 25 degrees Celsius or at 250 degrees Celsius, and what the values of delta G are at these temperatures. Let's look at the units of this problem. The units of temperature need to be in Kelvin, so we will convert delta S to kilojoules per Kelvin. For part A, 25 degrees Celsius plus 273.15 equals 298.15 Kelvin, and for part B, 250 degrees Celsius plus 273.15 equals 523.15 Kelvin. Delta S of the reaction will be 115 joules per Kelvin divided by 1,000 equals 0.115 kilojoules per Kelvin. For part A, plug your values into this equation. Delta G will equal 53.0 kilojoules minus 298.15 Kelvin times 0.115 kilojoules per Kelvin. This equals 53 kilojoules minus 34.29 kilojoules. The final answer will be 18.71, or rounded to 3 sig figs, 18.7 kilojoules. For part B, delta G will equal 53.0 kilojoules minus 523.15 times 0.115 kilojoules per Kelvin. This equals 53 kilojoules minus 60.16 kilojoules. The final answer will be negative 7.16 kilojoules. For part C, remember that a negative delta G indicates a spontaneous reaction. The negative delta G is achieved in part B with a temperature of 250 degrees Celsius. Does this answer make sense? Yes, it does, because 250 degrees Celsius is a higher temperature than 25 degrees Celsius, and the equation predicted that the reaction would be spontaneous at high temperatures. Calculate the standard free energy change for the following reaction at 25 degrees Celsius. CH4 gas plus 2O2 gas results in CO2 gas plus 2H2O liquid. We could do this problem one of two ways. We could solve for delta H naught of the reaction and delta S naught of the reaction, and then plug our values into the free energy equation, or we could use the free energy version of the products minus the reactants equation, which is the standard delta G of the reaction equals the product of all the coefficients of the individual products times their standard changes in Gibbs free energies of formation summed, minus the products of all the coefficients of the reactants times their standard changes in Gibbs free energy of formation summed. First, let's collect all the data we need in a table. You will find this data in an appendix in the back of your book. It will be labeled Thermodynamic Properties at 25 degrees Celsius. One thing you notice about this table is that all of the S naught values are positive, and most of the delta H naught and delta G naught values are negative. Why is this? Remember, the S naught values are experimentally determined absolute entropies, so they will always be positive, because this is just how they were designed to be. The delta H naught and delta G naught values can be positive or negative. We just have lots of negative values for this question. Except for the oxygen gas, notice that both of its delta H naught and delta G naught are both 0. Why is this? This is because O2 is an element, and this is its most stable form. If we had O gas or O3 gas in this problem, this oxygen atom and molecule have non-zero values of delta H naught and delta G naught, because these are not oxygen at its most stable form. Let's do this problem the easy way, by substituting in the values of delta G into this equation. The standard delta G of the reaction equals the product of all the coefficients of the individual products times their standard changes in Gibbs free energy of formation, summed, minus the products of all the coefficients of the reactants times their standard changes in Gibbs free energy of formation, summed. For this reaction, we have two reactants and two products. So the first part of this equation will be the coefficient of CO2 times the standard delta G value for CO2 gas plus the coefficient for H2O times the standard delta G value for H2O liquid. This equals 1 mole times negative 394.4 kilojoules per mole plus 2 moles times negative 237.2 kilojoules per mole, which equals negative 868.8 kilojoules. Subtracted from this number are the sum of the two reactant coefficients multiplied by their respective standard delta G values. This will be 1 mole times negative 50.8 kilojoules per mole for CH4 gas and 2 moles times 0.0 kilojoules per mole for the O2 gas. This equals negative 50.8 kilojoules. To find the standard delta G reaction, subtract the reactants from the products. This will equal negative 868.8 kilojoules minus negative 50.8 kilojoules, which equals negative 818.0 kilojoules. This reaction is definitely spontaneous because it is a combustion reaction.